Today we're going to talk about friction force. And friction is the F word in physics. It messes up all of our experiments, but it resists motion. It's why things don't continue going at a constant speed like they should with the law of inertia, because there's always some friction that slows things down. So there's two types of frictions. There's static friction that holds something in place. So if you're trying to push against something and it's not moving, it's static friction that's holding it in place. And then there's kinetic friction that if something's moving, it's kind of slowing it down, and it's making it so you have to keep pushing to keep it moving. And so the way we calculate friction, and it doesn't really matter if it's static or kinetic, is the same way. The force of friction is equal to this mu is called our coefficient of static friction. So that's a coefficient of static friction and times the normal force. Okay? And our mu's are usually, not always, but that's one way that we can check to see if our answers are reasonable. Mu is usually less than 1. Not always, but most of the time. This table shows a list of coefficients of friction. The mu s is our static friction, so that's when it's stationary. The mu k's are our coefficients of kinetic friction. And you'll see most of the time as we go across, not always, but most of the time, our coefficients of static friction are bigger than our coefficients of kinetic friction. And most of these, notice, are less than 1. But we do have this one that is bigger than 1. So these are things, this is the friction that's slowing it down. So if I was going to push a piece of glass on glass, I'd have to push it really hard to get it going. But then once I got it going, I wouldn't have to push as hard because there wouldn't be as much friction. And if we kind of look at these numbers, notice dry concrete has a higher coefficient of friction than wet concrete does. And that means that there's more friction with dry concrete than there is on wet concrete, which has an effect if we're trying to drive our car. Because if we're trying to drive our car, there's less friction on wet roads, and that's why there's more crashes when it's wet outside. But notice ice on ice, small kinetic friction. Teflon, hardly anything. Teflon has a very low kinetic friction. But notice these very rough surfaces, that's 1.5 is considered a high coefficient of friction. So the rougher our surfaces or the stickier our surfaces, the greater our coefficient of kinetic friction. So let's work out a sample problem. How much force is required to start moving a 25 kilogram wood cabinet across a wood floor? So if we're just going to get it started moving, are we talking about static friction or kinetic friction? Well, it's not moving yet, so we are talking about static friction. So our calculation is the same way. The force of friction is mu times the normal force. Well, we've got some information missing here. So we're going to do our free body diagram. We have gravity pulling it down. We have the normal force pushing it up. We are pushing it this way. And so if we're pushing it this way, friction is causing it to go backwards. And if we're just getting it to move, our friction force and our pushing force are the same size. And since it's not moving up and down, we'll find that our normal force and our gravitational force are also the same size. So our normal force is equal to our gravitational force. Our gravitational force is equal to our mass, 25 kilograms, times 9.8, which is 245 newtons. Okay, so take that, move that out of the way. So we know from our diagram that our friction force is equal to our pushing force because it's not moving. So once we find the friction force, we'll know how much we have to push it. Our force of friction is equal to our coefficient of static friction, 0.42, times our normal force, which we just found as 245 newtons. And so that equals 102.9 newtons. So that's how hard we're going to have to push it just to get it started. Okay, but how fast are we going to have to push it to get it to go at constant speed? Very important to know. You really want to look for that phrase, constant speed, because when something's traveling at constant speed, that means that there's no acceleration. And if there's no acceleration, there's no net force, which means all your forces balance out. And so not moving and constant speed give us the same situation where our pushing force and our friction force are again going to be equal to each other. So the pushing force is equal to our friction force, which is equal to mu times the normal force. But if we're moving at constant speed, now we're moving, and we're going to use our kinetic friction. So this is the same setup that we had right here. We've already found our normal force. So our friction force, instead of using the 0.42, we're going to use 0.30, which is our coefficient of kinetic friction. And we're going to multiply it by our normal force, which we found was 245 newtons. And that's going to give us a much smaller force. It's 93.5 newtons. So it does not require as much force to keep it moving as it did to get it to move. Oops, I misspoke. Instead of 93.5, that is going to be 73.5. I thought that number looked. So what happens if we push it with a force of greater than 73.5 newtons? Let's say we push it with a force of 100 newtons. Okay, is that going to change our kinetic friction force? The answer is no. So our friction force is still going to be the 73.5 newtons. Okay, so now we have a net force. And our net force is going to be in the direction of the bigger force. So we're going to have a net force in this direction, which is going to be the 100 newtons minus the 73.5 newtons, which is 26.5 newtons to the right. So now that we have a net force, we also have an acceleration, because remember, our net force is our mass times acceleration. So it's 26.5 newtons, which is equal to our mass. Hasn't changed, still 25 kilograms, times our acceleration. And so we will find that our acceleration is 1.06 meters per second squared. So now our box will accelerate, and what we see is the acceleration that actually happens.